You made it to day 4 of your challenge, of your 5-day challenge. If you guessed E2 for this specific reaction, you are correct. Let's go ahead and draw a general mechanism here. I'm going to have Br as our leaving group, and our hydrogen is going to be anticoplanar, and I'm going to make this a secondary alpha carbon. We need to have a hydrogen here on the beta carbon. We're going to react it with some base, and I like to draw a negative charge on this base. I put B for base because typically you need a very good base for E2. We're going to deprotonate, push down to make an alkene, kick out our leaving group. All happening at once. This reaction is concerted. So we have this transition state where this base is deprotonating it while the double bond is forming, while the leaving group is leaving. A lot going on all at once. I remember that this makes alkenes because E2, think about alkenes, has 2 E's. It's the best way for me to at least to think about it. Another thing you'll notice is that my product, this alkene, doesn't have that wedge anymore. This would be incorrect to draw. Remember that this carbon here is trigonal planar, and so we need to draw this flat. There are ways you can draw alkenes with wedges and dashes, but just don't. It's a good way to get things wrong, and unless you're properly showing why it's drawn this way, it will only cause confusion and make you lose points. So the way I like to remember it, anytime you have an alkene, draw all the lines flat. Don't draw them with the wedges or dashes. So this alkene is flat because that carbon is trigonal planar. Let's now dive into our specific example. Now our leaving group is here, and if I label our beta carbons, they're here and here. Now I'm going to actually label this second one in green. And so the red one here has this proton that is going back, and we know that we need that proton to be opposite of our leaving group, so the red beta carbon won't work. Does the green beta carbon have a proton that's coming up towards us? It does. Cool. Now that should be enough to keep going. We don't have a tert-butyl group on here that would cause the ring to not be able to flip. But let's, just in case you did do it, let's go ahead and draw this in its chair form so we can also analyze it the same way. Our leaving group, we would always want to put it in an axial position. It's going down, so I just choose one of the carbons where it's going down. It also has a methyl group, okay? And on our red beta carbon, we also have another methyl group that is going up. There's that one. And then on our green beta carbon, we have protons. Cool. We're just going to draw the one and we're going to use. It should be opposite and anticoplanar with the bromine. When I say coplanar, it just means that this hydrogen, carbon, bromine, this here has a 180-degree dihedral angle. You can get really crazy if you'd like. You could build the model, which isn't crazy actually. You could draw the Newman projection. I know you guys love Newman projections. I'm kidding, I'm being sarcastic. But it actually will clearly show you that the hydrogen and bromine have a 180-degree dihedral angle. Okay, so knowing this, we can go ahead and draw our mechanism. Now we can draw the mechanism just from the top here. So I'm going to do both, okay? So I've got my sodium ethoxide. This oxygen will pick off that proton, electrons will fall down, and the bromine will kick out. We will then have our 6-membered ring that didn't change. This methyl group on that red beta carbon didn't change. We have a double bond, and we've lost our bromine, but we still have a methyl here. It started out as optically active, and our product is optically active because we do still have a chiral center, and it's right here. And no arrows were drawn to that, so we keep it chiral. And it is optically active. Didn't switch. Now, for the bottom, we can draw the same mechanism. We can deprotonate this proton here, electrons fold down, and kick out our leaving group. We'll extend our arrow up to the top here. Now, when we get into the notes for the E2 reaction, you're going to find that you might need different notes than I'm writing here. So I'm just going to give you some things you can kind of think about. For the stereochemistry, we're really looking at if an E or a Z or a cis or trans is favored. And remember that E2 reactions, they happen all at once. It's concerted, and they aren't reversible. We're going to be forming the kinetic product. So it's the one that forms the fastest. And so knowing this, the key here with stereochemistry is this beta CH bond, okay? So this needs to be anti-coplanar. To our leaving group. And you can go into our lecture videos where I actually go through a series of practice problems, a little more in depth than maybe we would in person, but I thought it was useful. Now you only need to worry about anticoplanar if your alpha carbon and your beta carbon are chiral. Or if your alpha carbon and beta carbon are in a ring. All right, who made these reaction sheets? I'm running out of room already. Regioselectivity, this is where in the molecule. Where in the molecule is this happening? Okay, are you going to form a constitutional isomer where the alkene is on a different position? Again, this comes down to the beta carbon, this beta hydrogen idea. So if we look at our specific example, notice that the red beta carbon did not have a hydrogen that we could deprotonate. So our regioselective reaction occurred with this other beta hydrogen, this green one. Well, I just drew blue. So regioselectivity is where at in the molecule is the reaction going to form? Are you going to get a different constitutional isomer? So this really depends on where the beta hydrogen is, okay, and which one you can use. So let's actually write, maybe find the anticoplanar beta hydrogen. Again, you might find yourself writing some different things here for regioselectivity and maybe looking at those lecture videos and adding in very specifics about this anticoplanar rule. The best solvents here are polar aprotic. Think about acetonitrile or DMSO, or in this case we use acetone. Now you can use polar protic solvents. It just slows down the rate some. The key is the strong base. This is pretty low on the priority scale, okay? If a base is really strong, it won't wait around, okay? And also we have a lot of base. Typically you use excess. We just don't write this in. It's kind of assumed for E2 reactions. Anyway, polar aprotic is favored for E2, and this is because it doesn't inhibit this O- nucleophile, or in this case, a base. Okay, remember polar aprotic, no hydrogen bonding. But again, you may see examples where with polar protic, the key is if you have a good base. So the notes here there's many that you can write, and again, this depends on what you need to remember this. I want to make a note about the secondary carbons with leaving groups. We know that this competes with SN2, which makes all of this stuff confusing. So in this case, if you have a base that can do E2, E2 is preferred. It will be favored. And actually in this reaction, the alkene you form plus the other product you get from SN2, oh, I could have drawn that wedged. That would have been fine. There's no chiral center here. 55% and 45%. So the E2 is still preferred. However, you still get some of that SN2. So the reason I'm bringing this up is because typically, if you have, why can't I get this a different color? Bam. If you have a secondary carbon with a leaving group, E2 will be preferred as long as base is strong. So think E2 bases. Okay. Another note you might want to write here is that potassium terbutoxide, which is the super bulky base, is kind of a special case here, and it will typically form the less substituted alkene. One way I like to think about it is it picks the easiest H to access. So we're looking at the beta carbon that is least substituted. You might then want to write an example of this and showing that for potassium, or this one's just terbutoxide, will give you, in some cases, the least substituted alkene. It just depends on your starting material. So you might want to write a couple specific notes. You might run out of time on the exam if you don't take time to organize your notes. You can use Google, you can use the internet, you can use your book, you can use your notes. This is one of the benefits of being online with me. And the key here is, though, if you don't take the time to write out your reaction notes, you will likely run out of time on this next exam. There's a lot of concepts to tie together, and so I highly suggest taking time to fill out this last notes section and really maybe write some specific examples to help you remember the E2 reaction and some of the caveats that are involved here. So, all right, with that, that's it for our day 4 reaction sheet, and I will see you for day 5. All right, one more day, and there you have your reaction sheets, and you should be feeling more and more ready for the exam next week. Hopefully this is helping. Anyway, I'll see you guys in the next video.